Hi there and welcome to this video for Senior Physics on Nuclear Physics. In this video we're going to run through a review of the properties of radioactive particles. Now basically the whole sort of history behind radiation happened towards the end of the 19th century, and we all know the stories of Becquerel, Curie and Rutherford leading into Niels Bohr, etc., etc. Basically, they were the pioneers of our idea of radiation, and we know that Ernest Rutherford, who won a Nobel Prize for chemistry, did a huge amount with nuclear radiation when he was using his gold leaf experiment. Now remember, he was doing the gold leaf experiment to prove J.J. Thomson's model of the plum pudding idea, the idea that each atom was made up of was positive, and then it had these sort of negative particles engaged inside. And in that model, remember those negative charges were randomly placed. But in that model, he actually used alpha particles. And what we'd like to do is just recap on the properties of these alpha particles, these beta particles, and these gamma particles. And what he noticed was that they have varying penetrating effects. Now the penetration effects of radiation or radioactive particles can be identified using this very simple diagram you can see in the bottom corner here. Now the least penetrating is going to be your alpha particles. They will basically be stopped by something as thin as paper. Now this idea of penetration is really interesting, especially when you look at the idea of radiotherapy or using radiation within the medical field. Because if you're trying to get inside the body, then you want to have something which is going to penetrate and have the effect of causing an effect within a tumor or a cancer cell or whatever you're trying to manipulate with that radiation. So alpha particles, although have a really good ionizing effect, basically will only get through very thin particles. So it's almost skin deep. That's as far as it will go. It won't penetrate any further. So if you've got something like a brain tumor, there's no way alpha particles are going to work, even though you might think because of their ionizing ability they'd be better. So alpha particles can only get through very thin areas. That's then followed by beta particles, which can get through paper, metal, but again, they're only going to be foils. They're basically going to be able to get through substances where their particles are compacted together quite tightly, but they're only going to be quite thin. Their penetrating ability will not go through thick substances where the atoms are closely compacted. And it wasn't until Paul Villard in later on discovered gamma rays. And gamma rays, as we know, they're the most penetrating out of all of the radioactive particles. They can actually get through quite thick layers of concrete, lead, and steel. And that's why when we look at nuclear power and when we're trying to remove any of the nuclear waste, they're often stored in lead-lined concrete containers because it's the gamma radiation which can actually penetrate through. That's why they've got to be thick. If gamma wasn't there or wasn't liberated, then obviously we wouldn't need to actually store these waste products from radioactive power in these containers. And this is probably our big problem behind what do we do with that waste once we use it. If we were able to store them quite easily, then nuclear power probably would be used a lot more than it is today. So we've got these three main particles. We've got alpha particles, low penetration, beta particles, little higher penetration, and gamma particles, which has got very high penetrations. But what we also need to look at is what are these particles? Now we've done this before lower down in our schooling, but just to recap, if we look at alpha particles, they're made up of 2 protons and 2 neutrons. They represent a helium nucleus. Now I must stress here, they are a helium nucleus. They are not a helium atom. There are no electrons which are involved in the production of this particle. Because there's 2 protons, it has a positive charge. Okay, so its overall charge will be +2. It's a lumbering giant when it comes to the radioactive particles. It only has 10% the speed of light. And as we know, its penetration can be stopped by only a couple of sheets of paper. So alpha, positive, big, heavy, slow moving. Then we've got the beta particle. Now the beta particle is predominantly an electron. So it virtually has no mass. I won't say it doesn't have any mass, but it's so small that it's unaffected when we're looking at with respect to atoms. I mean, in the size of an atom, it's tiny. It has a negative charge, and it's traveling at 90% the speed of light. So it's a hell of a lot faster than the alpha particle. So we've got a small, negatively charged, fast-moving particle, and as we know, it can be stopped by a couple of sheets of aluminium or by thick, centimeter of wood. Finally, we've got gamma. Gamma is pure energy. So there is no charge which is present on the gamma particle, traveling at the speed of light, and we find it at the far right-hand side of the electromagnetic spectrum. So basically isn't a particle as such, because it's in the form of energy, and it can be stopped by thick layers of concrete or lead. Now, before we go any further, we sort of need to think about, well, if there's only protons and neutrons in the nucleus, where does the electron come from? And that's a question a lot of my students sort of ask, and they say, well, if beta's throwing out an electron, then it must come from the atom itself, and the atom is breaking down. It's not, it's the nucleus. And we need to go back to this equation. Now, this equation shows a neutron, which is shown on the left-hand side in yellow, has a mass of 1 and a charge of 0. Now, a neutron can break down into a proton and an electron. So if we've got this instability within the nucleus, this neutron can split up into a proton and electron. How it does it? No idea. When it does it? No idea. The fact is, that's how it does. And what it does is that neutron then will spit out this proton, and it will spit out this electron from the nucleus. So try and get into your head, get away from this idea when we're looking at nuclear physics of atoms, and deal with just the nucleus, hence the title of the topic. Where does that beta particle come from? It's that spitting out of the electron from the breakdown of that neutron. Okay? And then that makes sense. We've also got those protons which are going to make up the alpha particle. That alpha particle obviously will be made up of those 2 protons and 2 neutrons which are joined together, hence the helium nucleus. They're spat out from the nucleus, and then we're leaving behind that electron as a beta particle. Obviously, when we release these particles, energy is going to be delivered, and that energy is going to be in the form of gamma radiation. Okay, so I do hope that you found that useful. It's sort of a recap on the material that we've studied before, but I think it's important that we get this into our heads right early on in the course, so that when we start manipulating and saying, well, it liberates this alpha particle or a beta particle, we know exactly where it comes from, and we know how we can use it later on in the medical field. Okay, well, I hope you found that useful. Thank you for joining me, and I look forward to meeting you again in our next video. Bye for now.